this project is on the analysis and modeling of pulsar data from the NICER X-ray telescope on the International Space Station. Background. X-rays are high-energy invisible light, ranging from 100 to 100,000 electron volts per photon, compared to visible light 1.63 to 3.26 electron volts per photon. So in the electromagnetic spectrum image on the right, you can see that gamma rays are shortest, X-rays are a little longer, and then you keep going along, you have ultraviolet, visible, infrared, microwaves, and eventually radio waves. Also, gamma rays and X-rays can only be seen through satellites or by going into space, as long as they are emitted from space. Many of these remnants emit X-rays. Even black holes, which do not emit any light, can cause the emission of X-rays when gas heats up as it's being pulled into the holes. For example, in Cygnus X1, there's a blue supergiant star that is emitting gas, which is being pulled into a black hole. As the gas gets pulled in, it becomes extremely hot, and as a result, emits X-rays. Background on NICER. The Neutron Star Interior Composition Explorer, or NICER, is an ISS payload studying mostly neutron stars. Typically, each NICER observation lasts just a few thousand seconds. These observations are so short because NICER is on ISS, which has rotating solar panel that can cause the orientation to go wrong. Plus, ISS is in low Earth orbit, so it often passes through Earth's shadow, and at these times the solar panels do not work. However, NICER has excellent timing resolution and gathers photons over a large area, like almost twice as large as the effective area of another well-known X-ray telescope called XMM Newton. Analyzing NICER data. NICER records time and energy data for each photon and bins it in one of these variables. That means it lets the input be that variable and takes each cluster of data that's like packed near each other and turns it into one representative value. That makes the big data much smaller and easier to understand. In a light curve, check the image at the bottom, the data is binned in time with the energy range as an additional input. The output is photon frequency. You see it recorded as rate in counts per second. The counts are just photons. In the spectrum, the data is binned in energy. The output is light intensity in photons per kilo electron volt per second. And at the bottom, the data is fit to a series of models, and at the bottom, you'll see the residuals. These are the errors between the data and the combination of models. And these errors are magnified by a goodness of fit value called chi-squared. And then at the bottom, when you see all those errors, you can see the dips and the jumps. These are the spectral lines, the emission and absorption lines. Analysis threads. To do our analysis, we use the NICER analysis threads over here. These are really good because they're easy to understand, and all the data is public except for the most recent data. So it is relatively easy to use. Now here is some sample data. Cygnus X1. The energy range is 212,000 electron volts, time bin size is 1 minute for the light curve, and we have that for all our sample data. We have the light curve up top. Then the thermal energy emitted is 1649.21 plus or minus 187.5 electron volts, and that's a measure of the temperature of Cygnus X1. And now we have hydrogen column density. That is the amount of hydrogen that is in the area being analyzed per square centimeter. And flux density is the power of the emitted light per centimeter squared. So the spectrum is down there, and you see the spectral lines jumping. Now, this may not be a good fit, but don't worry about that. Now, we look at the unique pulsar called PSR J2021 plus 4026. This is a radio quiet gamma ray / X-ray pulsar. That means it can be analyzed through X and gamma rays, which it emits, but it does not emit radio waves. This is the first and only isolated gamma ray pulsar known to have varying radiant energy flux over time. So it goes up and down, so it changes, does not stay the same. The graph of the energy flux over time is shown. NICER has observed PSR J2021 plus 4026 230 times since December 2018, and here's a link to the light curve repository. These are all gamma ray light curves, and this energy flux graph is for gamma ray flux. Now here's some sample data on PSR J2021 plus 4026. So here we have the light curve. The hydrogen column density is important because this is a measure of the amount of gas that is in the pulsar. And that's a good estimate because most of the gas is hydrogen. And so here's the spectrum. We fitted the data in various models. So one of the models we used was black body. And this is a good model because the X-rays come from the surface of the pulsar, which emits radiation like a black body. That means it absorbs almost all light that hits it, converts that light into heat, and emits that heat. The black body model gives this thermal energy, which is a measure of the temperature. Next steps. After this, I'm going to analyze the remaining X-ray NICER observations for PSR J2021 plus 4026, then describe the gamma ray behavior of PSR J2021 plus 4026 during these time periods, then compare the changes in flux, temperature, and hydrogen column in the X-ray versus gamma rays. Thank you to Ariana and the rest of the N3 team for giving me this incredible opportunity, and to Pablo Parkinson for his support during this project.